Hello. Today we're going to show you how to create your own custom Llama 3 based chatbot using vLLM as the inference framework. vLLM is a very popular option for inferencing. Specifically, it's a library designed for inference and serving of large language models, making it perfectly suited for Llama models from Meta, which are some of the best open source models available. We're going to take that entire system and run it on Google Kubernetes Engine. By the end of this tutorial, you'll know how to fully produce a Llama 3 chatbot, and since we're using Kubernetes, you could potentially run it on any cloud platform. The concepts we'll cover are highly portable to other environments. So we'll have this vLLM system running on Google Kubernetes Engine, and we'll also use Streamlit for our AI interface. Streamlit is a user-friendly option for developing web applications, especially those that are data-centric. The best part, we'll only need a small amount of Python code for our Streamlit application. So let's dive right in. We'll start a new Google Cloud project, navigate to the Kubernetes Engine page, and enable the API. Once the API is enabled, we'll go to the clusters page to create a cluster. Here's a key point. Our architecture will greatly benefit if our inference can use some kind of accelerator. By choosing a model that's not too large, we'll be able to use NVIDIA GPUs like an L4 for our inference work. Now, despite what you might think, autopilot mode on Google Kubernetes Engine, which is a more opinionated cluster approach, does support GPUs just like standard clusters. It simplifies a lot of the setup. We don't have to design our own node pools or deal with complex configurations. So we can stick with the defaults and simply click Create Cluster. Once the autopilot cluster is ready, we'll begin our deployment work. We'll separate our project into two components, our Llama 3 inference and our Streamlit application, the chatbot itself. A great way to work on this code and manage resources is with the Cloud Shell IDE. Let's open that up in a new tab. Here we'll create a new repository for our project. And don't worry, we'll share all the code in the video description. Let's start by creating a demo file to house our Llama model. This will serve as our deployment resource. Looking at the high-level configuration, we'll specify a namespace and a name. Since we're just testing, one replica is sufficient. Next, we'll need to define a spec for our pods. It's crucial that we run this on an L4 GPU, which can comfortably handle our Llama model with around 8 billion parameters. To ensure our deployment runs on an L4 GPU, we'll specify a node selector with the key cloud.google.com/GKE accelerator and set it to NVIDIA 14. We'll also add a generic toleration for nodes with NVIDIA GPUs. This way, if there are nodes that only accept pods explicitly requesting GPUs, our deployment will still work. Now let's define our containers. It's great that we can use the vLLM Docker container. According to the documentation, there's an official Docker Hub repository we can pull from, which provides GPU capabilities by default. While there are TPU image options, we'll stick with GPU images that utilize the OpenAI interaction format for our chatbot. This open standard is something we can adopt, even though we're not using an OpenAI model. Now that we've specified our image, we need to configure additional settings. Specifically, we must set resource requests and limits to ensure our deployment schedules to a node with an available GPU. This is the critical piece for our deployment. But wait, the documentation also mentions that we need to specify our model and possibly a Hugging Face token. We'll skip caching the model locally, so it'll download each time we run it, no big deal. We'll also skip any network optimizations for now. We really just need to provide a few arguments and set up an environment variable. This should suffice for specifying the model. Since it's a gated model, we'll need to include our Hugging Face Hub token as an environment variable. While we could use a secret for better security, we'll supply it directly for simplicity in this demo. As you might have guessed, our Llama model will come from Hugging Face. Let's head over to their homepage to find it. Under the Meta Llama models, there are plenty of options. Our L4 GPU can comfortably handle an 8 billion parameter model, but if you have access to a larger GPU, you might opt for a larger model. The Llama 3.1 model with 8 billion parameters, fine-tuned and widely adopted, seems like a solid choice, so we'll go with that. To access it, you'll need to accept the terms and fill out a form. Keep in mind, the acceptance process might vary depending on factors like your country. Check your settings to track the acceptance process for the Llama 3.1 models. Meanwhile, we can generate an access token for our environment variable. A read token suffices since we're only downloading weights. Copy it and set it as our Hugging Face Hub token. If you're deploying something more production grade, it's best to use a secret for this purpose. As expected, the approval happened within about an hour, not too bad. We should now be ready to test our model with that Hugging Face Hub token, which we must keep secure. First, let's set our project. We have the Llama 3 vLLM project, and we need to authenticate with our Kubernetes cluster. All right, let's proceed to create our new Llama endpoint and see if any adjustments are necessary. In autopilot mode, we don't have node pools idling for our workloads. Instead, resources are dynamically provisioned. So it's normal to see a pending status for a little while. Let's ensure there are no underlying issues by examining the pod. After checking the events, we see that a scale-up of an L4 is set up, simply waiting for the node to be ready. We can see the node is coming online. It's been up for about 6 seconds. With our pod running, let's check the logs to confirm everything is operating smoothly. We might not have any logs, but that's acceptable. We're running on port 8000. Our image is quite large, about 8 gigabytes, but it appears to be working. Let's test it by running a port forward to this port and see if we can access it from our local machine. We'll hit localhost at port 8000 to verify it's running correctly. We can use an example curl command to test it. Looking at it, it seems we forgot to replace the placeholder model. Let's return to our model deployment and fix that. We're attempting to use the Llama 3.1 model. It turns out it's not accepting this argument format. Let's add an equals sign here so it doesn't split the argument. We can also adjust the deployment strategy to deploy quicker. With this recreate strategy, the pod will be automatically created and will continue running on the GPU that's been automatically configured for us. Let's make sure the logs look good before we do the port forward again to test the model. Our model appears to be functioning well. Now let's try out this curl command, making sure to swap in the actual model name we're using. Since this is a fine-tuned model, it will respond best to specific questions rather than completing partial sentences. But it seems things failed when we tried the port forward, and we had a pod restart. Why did that happen? To potentially fix this, let's create a model cache directory so we don't have to keep re-downloading our model whenever we face issues. Let's implement that with a quick update to our Llama specification. We'll add around 32 gigabytes of persistent volume claim to our pods. We need to mount this volume at the directory we looked at earlier. With our persistent volume claim implemented, our model will be up and running and we can start testing it shortly. We'll do this using a port forward. However, it looks like we have another error to handle. The simplest solution is to avoid this massive 132K max sequence length and simplify it for lighter memory requirements. All we need to do is add an argument here, like max model length. Setting it to something like 8K should be fine. What's nice is that we've cached the model download, so this restart will be quicker than before. Now, as we're reviewing the logs again, it's crucial to ensure we're using the GPU here. Otherwise, our inference will be extremely slow. So when you see platform CUDA, you know we're on the right track with the automatic platform selection. Now, this is a third times the charm moment. It certainly seems that way as we're getting some excellent application startup messages. We'll need to reinitiate our port forwarding, but this time, I believe we can successfully test and use this model. And after a few seconds, we're getting a really meaningful response here. You can see we have a couple of options. We had a total of about 262 tokens, including the prompt. This is a cohesive and sensible response, so I think this piece of our puzzle is now officially complete. We're all set with the vLLM setup. Next, let's set up our Streamlit system. Importantly, we'll be making calls from our Streamlit chatbot to the vLLM. So we need to ensure our Llama service is actually exposed. That is, we want to create a service for the chatbot, and that's going to be straightforward. We'll add one more YAML resource to our Llama file, naming it the vLLM Llama service. We'll use TCP port 8000 for HTTP, matching the selector, the label we have in our deployment. We can see the service has been created. If we describe the service, we should be able to see some endpoints here, which basically means some backends that we're actually serving from. So I think we're all set there. Next, we want to create our Streamlit application. We'll call this app.py, and it will be Python code. Since Streamlit isn't the main focus today, we'll just paste in the code here. Notably, we need to define some variables up front about our service, and then we create this OpenAI client using the OpenAI Python SDK. With our Streamlit app, we're basically going to have our system message and then trade requests and responses between our user and the assistant. It will basically have this session state that's going to store those different messages. Then we need to package this application. Let's create a Docker file using a simple Python base image, perhaps Python 3.12. We'll set a working directory, copy in our requirements, which we'll set up shortly, install them, then copy in our application code and run everything with the Streamlit command. For the server port, we'll decide to do 8501, which is kind of a standard for Streamlit. And we want to allow access from any client, so we'll set the server address to 0000. Finally, we're going to skip cores for simplicity in our demonstration. Now, we need a place to push this image. Since we're already in Google Cloud, we'll use the artifact registry. You could use a different system like Docker Hub or Artifactory, but we'll stick with Google Cloud for consistency. Our Kubernetes Engine instance is in the US Central Region, so for performance reasons, we'll co-locate our artifact registry there. Let's build and push our image to this repository. We'll run a specific command in our IDE, push to this path, name our container app, and tag it as latest. We haven't set up our requirements file yet, so let's do that. We'll specify Streamlit, aiming for at least version 1.44.1, which is the latest at the time of recording this video. We also need the OpenAI library. Let's ensure we have at least version 1.70.0. All right, let's try building again. Since the build is successful, we'll push it to our registry so it can be used as a new Kubernetes service. Once the image is pushed, we should be able to see it in our repository here. All right, so next up, let's go ahead and deploy this to our Kubernetes cluster. We're just going to bring in some code without diving too deep into Kubernetes, just to stay focused on our main goal. What you want to ensure in this YAML file is that you have your project ID and the full path to the image. We can get that by going to the image here and copying this entire path. This path includes a long tag at the end, but we'll skip that and just use the latest image. That's how we tagged it when we built it. This deployment looks a lot like the one we had for Llama, and that's because we're simply running a Docker container and exposing some ports. We don't need persistent volumes or anything like that here, so let's apply this to our cluster. Since this VM doesn't need a GPU, it's going to provision pretty quickly. It'll give us a couple of cores and a few gigs of RAM. As we did with the other service, we can test this out by doing a port forward. One cool thing about the Cloud Shell Environment IDE is that we can use the web preview feature. Let's change the port to 8501 and preview it. Keep in mind, though, that these web previews may not support features like WebSockets, which might prevent our app from working fully. But let's give it a try. All right, looks like we have an error coming back from our vLLM instance. There might be a typo. Let's take a look at what we're trying to hit. Yes, it looks like we have a little extra meta in here. Let's tweak our application environment variables. This gives us a good excuse to rebuild and repush our model with the new environment variable. Now, to get this to pick up the latest image, we can delete the pod. Since we're using the latest image tag, deleting the pod will prompt Kubernetes to pull down the new image if it is changed. We'll need to rerun our port forward command here. After about 45 seconds or so, our pod is now running. We can check the logs to make sure, and indeed, it looks like things are running quite nicely. We've got our port forward going, so let's refresh our app in the new tab and give this a try. All right, we're still getting the same error message. Even though we rebuilt and restarted the application, we need to debug this a little bit. Indeed, it shows us that we have the right environment variable here, but we've overridden that in our YAML file. So we need to change that here. Again, we have both the default in the application code and potential overrides in our environment variables. So it looks like we have to fix both sides. Since we didn't change the deployment strategy, it's going to create a new pod before it deletes the old one. That means we don't have any downtime for our Streamlit app. Our new system is running. We can check the logs again. Looks good to me. Let's give this another try. And I would say our chatbot is working quite nicely here. Of course, because we've custom developed this chatbot application, you can do lots of customization. Maybe you use a fine-tuned model, for example, and we have tutorials on this channel that can walk you through how to do that fine-tuning. Maybe you have certain integrations with other systems that you have or some personal data or applications. All these sorts of things are possible since this is a custom application. Now you'll probably want to use some production grade networking here, so let's just finish up by doing exactly that. Once the load balancer service gives us an IP, we can access our app on that, and we won't run into any pesky networking issues like we had with our preview networking with our Cloud Shell IDE. Just keep in mind that as you productionize an app like this, you're typically going to want to use something like Terraform instead of manually creating all these resources like we did in the video today. If you'd like to support the channel, consider starting a free trial of our new design tool, which is linked in the description, and let us know what you think. We'll include all code and the diagram file in the description as well. If you have any questions, please post them in the comment section, and we'll do our very best to respond. Thank you very much for watching till the end, and please enjoy responsibly.